Hi, today we are going to take a look at a very famous and interesting problem in the domain of probability, that is, the Monty Hall problem. This is in regard to EE230 Probability and Random Processes course, lecture number 5. Now let us look at its problem statement. Problem statement is that you are on a game show, being asked to choose between three doors. Behind each door, there's either a car or a goat. There are two goats and one car. You choose a door, but you are not shown what is behind that door. Instead, the host, Monty Hall, picks one of the other doors, which he knows has a goat behind it, and opens it, showing you the goat. You know, by the rules of the game, that Monty will always reveal a goat. Monty then asks whether you would like to switch the choice of door to the other remaining door or to keep it. Assuming you prefer having a car, of course, more than having both, do you choose to switch or not to switch? Illustrating it, you can see in the diagram that, for example, if you choose door number 1, then, for example, Matty Hall chooses door number 3 and opens it and shows that there's a code behind it. Now, the question before you is, would you switch to door number 2 or would you stick to door number 1 to maximize your chances of winning a car? For most people, it would be very straightforward and they would say it doesn't matter because among the remaining two, it would be equally probable that it would be goat or a car, goat or a car. But surprisingly, the answer is if you switch, you would have more chance of winning the car. Let us see why. The crux of the problem lies in the fact that Monty Hall does not open his door randomly. The door he opens definitely always contains a code. Let's see its explanation. Let's assume that we choose door number 1 in our turn. Let H be the hypothesis that door 1 has a car behind it, and E be the evidence that Monty has revealed a door with a goat behind it. So probability of H given E represents the probability that door 1 has a car behind it given Monty has opened another door with goat behind it. This means that after Monty has opened the door with the goat behind it, what is the probability that door 1 has a car behind it? Simply, this is the probability in the game after the host Monty Hall opens door number 1 is there is a car or not. Using Bayes' theorem, we can say probability of H given E is probability of H to probability of E given H upon probability of E. Probability of E can be expanded into probability of E given H into probability of H plus probability of E given H complement into probability of H complement. H complement is just the complement or not H. Now we have the values. Probability of H is the prior probability that no one has a car behind it, and it will be uniformly 1 by 3 across all three doors before the event has occurred. Probability of H complement is 1 minus probability of H. So it is 1 minus 1 by 3, that is 2 by 3. Probability of E given H has occurred is the probability that Monty shows a door with a goat behind it, given that there is a car behind door 1. Now, this is always 1 because Monty always opens a door with a goat behind it. So, probability of E given H is always 1. Probability of E given H complement is the probability that Monty shows a door with a goat behind it, given that there isn't a car behind door 1. Now, this is again 1 because there is always goat behind the door that Monty knowingly reveals. So, in conclusion, we would say putting the values into the equation, probability of H given that E has occurred is 1 by 3. Notice that it would also have been the same if the event nothing had happened, just we had three doors and we would have been asked what is the probability that door 1 contains the car. This means that but what changes is that either door 1 Or for example, in the illustration 2 contains the car. Because once Monty Hall has shown which door does not contain the car, now you have only two doors. If, if we switch, then the probability will be 1 minus probability of h given a, that is 1 minus 1 by 3, that is 2 by 3. So the answer is that you should have switched to have greater probability of winning. At last, this is a slide showing Marilyn Bonswan, who is credited for making the problem famous. Here is an excerpt to a reply to a column by a PhD from a university in the US. Thank you.